Okay, so let's pick up where we left off. So we wrote the net ionic equation. So now we have the simplified equation. So we can now use stoichiometry to determine how many moles of oxalic acid were originally in solution. Okay. Oh, but did I write this? Hold on a second. I think I wrote something incorrect here. Oh, yes. So sorry, everyone. This should be 04. Please, let me correct myself there. Sorry, that looked weird. There's no way there could only be 2 oxygen atoms for oxalic acid. That, structurally speaking, that wouldn't make sense. Right? Because we should know this because we all oxalic acid did appear in the discussion last week. Okay. All right. So we know the volume and concentration of sodium hydroxide. Now we can calculate the number of moles of sodium hydroxide that reacted in solution. Okay. So we know that. I'm just going to keep writing the equation here so we get it in our heads here that a molarity equals moles over liter, which equals, we can say moles is equal to M times molarity times L. Okay? So the molarity of sodium hydroxide, 0.200 molar, or moles per liter. Okay? Now, we know that 1 liter, now we have 34 times the volume, 34 milliliters. So let's make sure we keep the right number sig figs here, 34.0 milliliters. And we know that we need to convert from milliliters to liters, and we know that 1 liter is equal to 1,000 milliliters. So this will help us cancel milliliters here. Liters will cancel here. And then we get our moles. So the number of moles here is 6.8, as we put in our calculator here, times 10 to the negative 3 moles sodium hydroxide. Okay, so let's move this over a bit so we can see it. All right, so that's how many moles of sodium hydroxide reacted in solution. So that's an important detail, right? Because now we can use the balanced chemical equation to figure out how many moles of this sodium hydroxide produce, how many moles of this reacted with oxalic acid. So if this amount of moles was needed to consume all the oxalic acid, we can determine how many moles of oxalic acid was originally present in solution. Okay, so 6.8 times 10. Oh, well, I should not actually use 6.8, right? It should be 3 sig figs. So we should actually, let's actually do that calculation here. 0.200 times 34 divided by 1,000. Okay, so it's 6.80. All right, times 10 to the negative 3 mole sodium hydroxide. So we know that for every 1 mole of sodium hydroxide, right, there is 1 mole of OH minus. And now in our balanced chemical equation, we can say there is 2 moles of sodium hydroxide per 1 mole of oxalic acid. And then when we do that, we solve for moles, right? Oops, I put oxalic acid. I didn't put 1 mole. Sorry about that. So we do 1 mole, because in our balanced equation we have 1 mole. H2C2O2. Okay? So we do, if anyone's confused about that, let's just look back up here on our chemical equation. 2 moles of hydroxide will react for every 1 mole of oxalic acid. So there's an imaginary 1 here. And then if we solve this equation, we will get 3.40 times 10 to the negative 3 mole C2, oops, not C2, H2, H2C2O4. Okay, so moles of sodium hydroxide cancel out, moles of hydroxide cancel out, moles of hydroxide cancel out here, and we get moles of oxalic acid at the end here. Okay. Now we have the moles of oxalic acid in the original solution. So now we need, we have the volume too, so using the volume we can now determine the molarity of solution. So in the beginning we just calculated 3.40 times 10 to the negative 3 mole oxalic acid. Okay? And then we divide that by 0.0250 liters of solution. So where did I get this number from? So when we go back, scroll back here, we see that our original solution of oxalic acid was 25 milliliters. So we got this number by dividing 25.0 milliliters by the conversion factor for liters, 1,000 milliliters per 1 liter, which equals this number. Okay, so if we solve that, we would get our original concentration of oxalic acid, which is 0.136 molar oxalic acid. Okay, so that's how you would do a typical stoichiometry problem with solutions. So it's a lot of steps, but if you take it step by step and make sure the equation is balanced, and but typically I would give you the equation, I think, but eventually you have to realize that you have solutions, you need to find moles, and then using the chemical equation, you can figure out the moles of the substance that you're trying to find a concentration for, and then use the original volume to find the concentration. Okay, so there's a lot of steps, but if you take it step by step and simply don't try to memorize what to do, it should make sense. Okay, so to wrap up this, let's go over one more dilution problem, because I feel like we didn't do enough of that. So let me erase this and do the dilution of one more dilution problem, and then we'll call it good today. And then in the next lecture, I'll go over one more stoichiometry problem with solutions. So we can look at we can see a different example. Okay, so let's just draw like a box here. Okay. So say I want to prepare a solution of sodium chloride with a concentration of 0.25 molar. And 250 milliliters. Okay. From a 3 molar solution of sodium chloride. Okay. So the easiest thing to do is use the M1V1 equation. So I'll do more examples with this. So in this case, M1V1 is our more concentrated solution. So we're going to do 3 molar here for M1. Okay. So this is M1, and then V1 is what we're trying to solve for, right? So we need to find V1 because we don't know the volume of that. Then M2 is 0.25 molar times the volume in liters. So we're going to put 250 milliliters. So let's put a dot here. So it's kind of, well, actually we don't need to put a dot. It doesn't matter. Oh, shoot. Yeah, that's good. Okay, but we need to also convert this, so 1 liter over 1,000 milliliters to give us liters of solution. Okay, so when we have 3 molar here, all right, so if we rearrange the equation, we will have V1 equals, so remember M2 here, so this is actually, sorry, let's just write notes here. M1's the concentrated solution, M2 the dilute, and then V2 the volume of the diluted solution. So V1 equals 0.25 molar times, in this case, this will reduce to 0.250 liters divided by 3 molar. So we just divided. So let me just put a 0 here. So it actually has proper sig figs. So usually when we make solutions, we want at least one decimal point. So 3.0. Molar here. See, the molar and molarity will cancel, and then we solve for volume here, and we get 0.25 times 0.250, and that will give us, we divide that value from 3.0, we will get a very not so even number, or 0.02083, and we're going to round it to 2 sig figs, so this will equal 0.021 liters. Or we could reduce this to say 21 milliliters. So we would take, so what this is telling us is that we're going to take 21 milliliters of this solution here, and dilute it to a new total volume of 250 milliliters. Okay, so that's what that means. So on exam, I would ask, how would you prepare the solution? You would have to first show your work to find the volume, and then you have to say in a sentence, I'll take 21 milliliters of the concentrated sodium chloride solution, and then dilute that to a new volume of 250 milliliters in a new flask. And that's how you would prepare a 0.25 molar solution from a 3.0 molar solution of sodium chloride. So typically, sometimes diluting something is easier than preparing a very small concentration of something, is because you can't weigh that small amount out on a scale. So it often becomes impossible to do that. So dilution is a very important skill. Okay, so let's end it there. We'll pick up more of aqueous solutions and aqueous chemical reactions in the next lecture, lecture 6. So I'll see you next time.